Uncover the true power of op-amps with me in this video. Forget the generic definitions you have here. Let's dive deep into practical applications that really matters. Ever wonder where to place an op-amp in your circuit? I have got the answers. Many tutorials out there focus on clichéd phrases like inverting amplifier or differential amplifier. In contrast, I'm bringing you 4 real-world applications of op-amps along with examples and insights. You will see how op-amps makes us able to build digital weighing scales, how they help us to precisely measure teeny-weeny currents, how op-amps help us to estimate temperature, and how op-amps makes us able to accurately transfer analog sensor voltages over long distances up to several miles. This one is my favorite. No need to fear math. I'm skipping the complex calculations and zooming in on the practical side. Stay with me on this journey through the essential details about the op-amps and ICs. Ready for a blend of theory and hands-on knowledge? Join me as we demystify op-amps and explore the magic of op-amps together. A big thanks to PCBWay.com for sponsoring this video. I'm proud to announce that the big sale of PCBWay.com is started. Now you can enjoy discounts up to 50% on high quality printed circuit boards. It's not just PCBs, all services are in. PCB prototyping, CNC machining, 3D printing, injection molding, vacuum casting. Countdown timer is ticking. Don't lose this opportunity and click the link below in description. Anyway, let's start our journey. Op-amps, operational amplifiers, they are not as difficult as they seem. To begin with, I'm gonna take a brief look at an ideal op-amp and its basic definitions. This is a schematic symbol of an op-amp. It's a triangle that has 2 inputs and a single output. The input with a minus sign is called inverting input, and the other with a plus sign is called non-inverting input. Even though the input impedance of an ideal op-amp is infinite, which means that the current flowing to these terminals is always 0, the input impedance of a real op-amp like this IC is not infinite. It's very high, but not infinite. This is LM741 op-amp IC, which is a general purpose op-amp. And this is its datasheet. On page 5, there's a table where you can find a parameter called IB, or input bias current, that indicates the amount of current flowing to input terminals of the op-amp inside the IC. It's very low. It's about 1.5 microampere. It's almost 0, so we will consider the current flowing to these terminals equal to 0 for simplicity. These plus V and minus V leads are indicating the supply voltages. In many cases, it is not necessary to determine them in a circuit diagram, but if it is needed in a specific application, we can use this schematic symbol instead of this. For example, if we need to determine the exact supply voltage for an op-amp, or if the supply voltage is not constant or something. An ideal op-amp has no supply voltage limit, but a real op-amp operates within a predefined voltage range. Look at this table on page 4. LM741 and LM741A operates on a maximum of 22 plus minus 22 volts, and LM741C operates on plus minus 18 volts. Also, there is another parameter here called input voltages. It's plus minus 15 volts for LM741, LM741A, and LM741C, which indicates the maximum and minimum voltage allowed to be applied to inverting and non-inverting inputs. The output impedance of an ideal op-amp is 0, which means that the op-amp can deliver infinite current on output. Even though a real op-amp has a low output impedance, it is not 0. So an ordinary op-amp IC like this one can deliver a few milliamps. Look here on page 5. The output short circuit current for LM741 is 25 milliamps, which is not much, let alone infinity. Op-amps can do many things, from simple to very complicated tasks. I'm gonna start from a very simple task an op-amp can perform. Application number 1, using op-amp as a comparator. One of the most simple and common application of op-amps is to use them to compare two voltages to see which one is higher. You may wonder why somebody should compare two voltages. Let's see some examples. This is a Hall effect sensor. Its job is to sense the magnetic field and present the sensor value at output pin in form of an analog voltage. By applying the power supply voltages to these terminals, the sensor starts to work and shows us the magnetic field strength at the output in form of analog voltage. Look at the voltmeter. In normal situation, the output voltage is something around 2.5 volts, which means that the magnetic field does not exist here. By putting a magnet near the sensor, the voltage at the output pin changes. One of magnet poles will cause the output to approach the source voltage, and other one will cause the out voltage to approach the ground voltage. A voltage comparator will be useful here to make a proximity sensor. If you apply a reference voltage, say 3.4 volts, which is more than the normal output voltage of the sensor to V1, and the sensor output voltage to V2, then it will compare two voltages and activate the output when V2 is higher than V1. In a normal situation, the output will be inactive because 2.5 volts normal output voltage of the sensor, which is connected to V2, is less than 3.4 volts reference voltage at V1. But when the north pole of a magnet gets close enough to the sensor, the output will be activated because in that condition, the sensor output voltage will get higher than the reference voltage. Look here. The reference voltage can easily be made with a resistor voltage divider. If R1 is equal to 2.2K and R2 is equal to 4.7K, then by using the voltage divider network equation, the reference voltage here at point V1 will be about 3.4 volts, which is more than the normal output voltage of the sensor, and it's okay for now. There are several ways to build a voltage comparator. However, using a single op-amp is more common. Using an op-amp as a comparator is very simple. You just need to connect no components to the op-amp. Yes, if no components is connected to the op-amp, it will operate as a comparator. We can use an op-amp like this to make a comparator. Just connect the sensor output voltage to non-inverting input and the reference voltage to inverting input, and it's done. The op-amp will compare two voltages on inverting and non-inverting inputs, then activate the output if the voltage on non-inverting input is higher than the voltage on inverting input. In this experiment, I'm gonna use LM339 op-amp IC. This IC. This is the pinout of the IC. There are 4 op-amps inside this IC on a single chip. I'm gonna use this one, so I have to connect source voltage to pin 3, ground to pin 12, and the sensor output to pin 7, and the reference voltage to pin 6. Then the output will be ready at pin 1. It's not working because of a specific characteristic of the LM339 IC. Before solving the problem, I'm gonna answer a question I guess you have in mind. There are a lot of op-amp ICs available in market with different features and specifications, including LM741, LM324, LM339, LM311, and many others. You may ask why I used this particular IC in this experiment. Good question. The main difference between these ICs is in their operating voltage, temperature range, cost, package, number of op-amps in a single IC, specialized features, etc. The answer to this question is the specialized features. You can use almost any op-amp IC to build a comparator, but if you look at the datasheet of LM339, you will find an interesting point. So this IC is specialized to be used as a comparator. Some op-amp ICs are general purpose, like LM741, LM324, but some others are specialized to be used in particular applications. For example, LM386, which is specialized to be used in audio amplifiers. LM339 is another example, which is specialized to be used as a comparator. The main difference between LM339 and general purpose op-amp ICs is in their output voltage form, which is digital open collector and can produce analog voltages, in contrast to general purpose op-amps which can produce analog voltages. So I decided to use this IC as a comparator because it is specialized to be used as a comparator. The output of this IC is open collector, so I have to put a 1 kilo ohm pull-up resistor here. The value of this resistor is not important because it just affects the brightness of the LED. When I put a magnet near the sensor, the LED turns on, which means that the output of op-amp is activated. And when I put the magnet away, the LED turns off. By the way, if you connect the sensor to an inverting input and the reference voltage to non-inverting input, then the output of op-amp will be inverted. I mean, the LED will turn on in a normal situation and turn off when the magnet is near the sensor. The output is inverted. This sensor is used in most refrigerators to detect if the door is open. See, when the door is closed, the magnet is near the sensor and the op-amp turns off the LED. In old refrigerators, mechanical switches were used to turn a bulb inside the refrigerator, something like these limit switches. But these magnet sensors are hidden, making them more clean and TD switches. Also, this mechanism can be used in many other applications. For example, musical boxes to detect if the box is open and similar applications. To describe how an op-amp can compare two voltages, I have to describe the main job of an op-amp. It's obvious that the main job of an operational amplifier, or op-amp for short, is to amplify the voltage difference between its non-inverting and inverting inputs. But the main question is how an op-amp can amplify the voltage difference between its non-inverting and inverting inputs. This is datasheet of LM741. Look at this parameter here. Large signal voltage gain, whose typical value is 200 volts per millivolt at room temperature. It means that this op-amp will amplify every 1 millivolt to 200 volts.
Here in this example, the voltage at inverting input is exactly 1 volt and the voltage at non-inverting input is 1.001 volt, which means that the non-inverting input is 1 millivolt higher than the inverting input. Since the gain is 200 volt per millivolt, the output must be 200 volts because the difference between inputs is 1 millivolt.
This is a common mistake. Most newbies think that an op-amp or in general an amplifier increases voltage, but this is not true. An amplifier just let a portion of supply voltage to pass to the output according to the input they get. So output of an amplifier can't be higher than the supply voltage.
Since the maximum voltage in the circuit is plus V, say 16 volts for example, and it's less than 200 volts, the output voltage can't get higher than plus V in theory, so the output must be equal to 16 volts. This situation in which the voltage at output must be greater than the supply voltage, but it is not, is called saturation. However, in most real op-amp ICs, the saturation voltage is about 80% of source voltage. If the supply voltage is equal to 16 volts, then saturated output voltage can't be more than 12.8 volts.
200 volts per millivolt is a high amplification gain, which means that if non-inverting input is a bit higher than inverting input, then the output will be saturated. In another word, the output is activated. The opposite is true as well. So if non-inverting input is a bit lower than inverting input, then the output will be saturated to minus V, which is negative supply voltage or ground. This is the comparator which compares two voltages and set the output to one of supply voltages according to value of input voltages. Anyway, a magnet sensor is not the only sensor which can be used beside the comparator.
We can use a potentiometer to make the reference voltage instead of using two constant resistors to get more flexibility in setting the reference voltage. Anyway, you can use a comparator beside an LDR to make an automatic night light. This is the pinout of the IC in page 3. Look here. When the light is on, the LED is off, but when I cover the sensor, you see the LED turns on.
Up until now, we considered the op-amp as a comparator. There is another usage of op-amps that is so exciting. Application number 2, using op-amps as a simple amplifier. One of most common uses of op-amps is to use them as a simple amplifier, also called non-inverting amplifiers. The main job of an amplifier is to make tiny voltages higher for ease of processing or measurement. I'm gonna explain where, why, and how to use an op-amp as a simple amplifier, but before diving into those topics, I'm gonna mention an important concept about op-amp based amplifiers before moving on. The concept is called virtual ground concept.
As I said a few minutes ago, the gain of this op-amp is 200 volt per millivolt, which is very high. Suppose that the supply voltage is 5 volt. Then, by writing this simple proportion, 200 volt is to 5 volt as 1 millivolt is to X, we can find the voltage that is supposed to be amplified to 5 volt. This op-amp is going to amplify 25 microvolt to 5 volt. 25 microvolt is very tiny. Actually, most signals and voltages in a real circuit are far larger than 25 microvolts. So this amplifier is not practical. We have to find a way to reduce and control the gain of op-amps. This goal will be achieved using the virtual ground concept. The virtual ground concept is so simple. It says that the voltage at inverting and non-inverting inputs of an op-amp must always be equal. I mean, the op-amp tries its best to make the voltages at these inputs equal by changing the voltage at output. This simple rule makes us able to build op-amp based amplifiers with the desired gain. This is the most basic amplifier we can make using op-amps. The voltage at this point is VO or output voltage. The voltage here is VI or input voltage. The voltage here is VA and the voltage here is VB. These two resistors here form a voltage divider structure. Notice that the current flowing to these inputs is negligible. By using the voltage divider equation, the voltage here at point A is a function of RF, RB and output voltage. If I assign 10 kilo ohm to RF, 1 kilo ohm to RB, then the voltage at point A will be a function of output voltage only. Suppose that the input voltage is 0 volt, then the voltage at non-inverting input of the op-amp is 0 volt because the input voltage is directly connected to non-inverting input of the amplifier. Based on virtual ground concept, the voltage at inverting input must be equal to non-inverting input, 0 volt I mean. Then the op-amp has to set the output voltage in such a way that makes the voltage at inverting input equal to 0 volt. Thus, the output of op-amp will be equal to 0 volt to make voltage at point A equal to 0 volt. Now suppose that the input voltage is increased to 0.1 volt. Then the op-amp has to set the output voltage in such a way that makes the voltage at inverting input equal to 0.1 volt. So by using the voltage divider circuit, the op-amp has to put 1.1 volt on the output to make the voltage at inverting input equal to 0.1 volt to make the voltages at inverting and non-inverting inputs equal. So the voltage at output is 11 times bigger than the input voltage. It means that we have successfully amplified the tiny 0.1 volt input voltage to a larger value 1.1 volt. In the same way, if I apply 0.2 volts to the input, the op-amp will set the output to 2.2 volts to make the voltage at inverting input equal to 0.2 volts. The gain of this amplifier is equal to 11. By changing the value of these resistors, we can change the gain. Actually, the gain is set by this formula. If you need to increase or decrease the gain, you can change the value of RF and RB. By the way, this resistor here, which is connecting the output to input, is called a feedback resistor.
This is the simplest use of an op-amp as an amplifier. Just apply a tiny voltage to input, then the amplified voltage will be ready at output. It's that simple. So let's move on to the next application. Now, just kidding. We are not moving anywhere before discovering practical application of the circuit. Actually, this configuration is used where we are dealing with tiny voltages. You may ask, where is there a tiny and important voltage in a circuit? One of the most common examples is the voltage across a thermocouple.
This is a thermocouple. When the temperature at this junction point, look here, increases, the voltage between its leads increases as well. To measure the temperature at this point, we have to read the voltage between its leads and do some calculations to achieve the right temperature. But there is a problem. I'm gonna connect the thermocouple to my multimeter and see what's going on. Some multimeters are able to directly read the temperature through thermocouple. Look here, this multimeter has an option on selector to read the temperature. Here, this one. Now the temperature here is about 23 degrees Celsius. If I heat it up using this lighter, the temperature increases. Look here. But this is not what I am looking for. I am looking for the voltage between these two leads. I need to connect this thermocouple to my circuit, not a multimeter. So I have to set the selector to the DC voltage measurement option. Now we have 0 volts here between these two leads. Let me heat it up. Yes, it shows a tiny voltage, a maximum of 10 or 11 millivolts.
The problem is that the voltage between its leads is so tiny, it's impossible to read it directly using ADC unit in microcontrollers. We have to amplify that. Since we have two leads here, the best option is to connect negatively to ground and positively to a non-inverting amplifier.
When the temperature increases, the voltage between these two leads increases as well. Since the maximum voltage I observed here is 10 millivolt and the reference voltage on most MCUs is 3.3 volts, I need to amplify this 10 millivolt to 3.3 volts. Thus, the gain has to be 313x. To achieve this gain, I will use 313 kilo ohm for RF and 1 kilo ohm for RB. Now that the voltage is amplified, we have a variable voltage from 0 volt to 3.3 volt, which can be easily read by any ADC unit.
Thermocouples are widely used in industrial equipment and their usage will be restricted without an amplifier. Anyway, we are moving on to the next application. Application number 3, using op-amp as a differential amplifier. The differential amplifier is a configuration of an op-amp that takes two voltages, multiply the difference between them by the gain and put the result on output. A non-inverting amplifier amplifies a voltage that is relative to ground, but the differential amplifier amplifies the first voltage relative to second. We will see what it is good for.
This is the configuration used to make a differential amplifier out of op-amps. It's very simple. Just apply differential voltage to these inputs and you will get the amplified differential voltage at output. This configuration will amplify the voltage difference between its inputs V1 and V2. For example, if the voltage at V1 is 0.62 volts and the voltage at V2 is 0.79, then the difference between these two inputs is 0.17. Let me assume that the amplifier gain is 10x. Then the voltage at output will be VO is equal to 0.17 times 10 equal to 1.7 volts. The gain is set by RF, RA, RB and RC subject to these conditions. Suppose that you are going to set the gain equal to 10x. One simple configuration will be RA equal to RB equal to 1 kilo ohm and RF equal to RC equal to 10 kilo ohm. By this configuration, the gain will be equal to 10x.
I know you are interested in knowing the application of this differential amplifier, where to use it, how to use it. I'm going to give you two practical examples. The first one is to measure the voltage across a current sensing shunt resistor. You may ask, what is a shunt resistor, what it is good for? Let's find answers to these questions.
These are shunt resistors. They are used to measure current. The distinguishing feature of shunt resistors is their low resistance value and high current tolerance. For example, this one is a 0.02 ohm 10 ampere shunt resistor. Also, this one is an SMD 0.43 ohm shunt resistor. The symbol used for a shunt resistor is the same as the symbol used for every resistor. Like all types of resistors, shunt resistors follow Ohm's law. So, when you apply a voltage to these resistors, some current will pass through the resistor. Also, when some current passes through a shunt resistor, a voltage will appear across the shunt resistor. The amount of voltage is directly relative to the amount of current flowing through the resistor and can be determined using this simple Ohm's law equation. Inside most ampermeters, there is a shunt resistor. You may find shunt resistors in different shapes, types, and sizes, but all of them are used to measure current. This is a volt ampermeter module mostly used in handmade power supplies like this one, and this is the shunt resistor inside this module. Look here. When the load draws current, this module measures the current by measuring the voltage across this shunt resistor. Look here. Inside most multimeters, there is a shunt resistor, sometimes more than one, which is used to measure current. I guess this is the first thing that came to your mind, to put the shunt resistor in series with the load like this, so the current flowing to the load is equal to the current flowing to the shunt resistor. One terminal of shunt resistor is connected to the ground, so we can measure the voltage across shunt resistor by reading the voltage at this point using ADC.
The concept is not wrong. Just put a shunt resistor in series with the load, then read the voltage across shunt resistor and calculate the current using Ohm's law. You may think about reading the voltage across shunt resistor using ADC unit of the microcontroller. At first glance, it seems good, but I have to say that there are two serious problems here. The first problem is the amount of voltage across shunt resistor. Since resistance of shunt resistors is typically very low, the voltage across a shunt resistor is tiny.
Assume that the MCU is operating on 3.3 volt and the ADC is reading the voltage in 10-bit resolution mode. So the minimum voltage the MCU can read is 3.2 millivolts. Assume that the shunt resistor value is 50 milliohm and the load is drawing current between 0 and 100 milliamperes. When the load draws 1 milliampere, the voltage across the shunt resistor will be 50 microvolts, which is 64 times smaller than the minimum voltage the MCU can read. Actually, this system will measure the current in 64 milliampere steps like 0 milliampere, 64 milliampere, 128 milliampere, 192 milliampere, etc. and can't measure values between these numbers. This is the problem. The maximum current the load draws is 100 milliampere, so this system will show only 0 and 64 milliampere and is not able to show other current amounts.
To precisely read the current, we need to amplify the voltage across shunt resistor. I know the load draws maximum of 100 milliampere and the shunt resistor is 50 milliohm. So the maximum voltage across shunt resistor will be 5 millivolts. Therefore, we need to amplify the voltage across shunt resistor, which is varying between 0 volts and 5 millivolts. On the other hand, the ADC unit of the microcontroller is able to read voltages up to 3.3 volts. So we have to set the gain to amplify 5 millivolts to 3.3 volts. The gain has to be 3.3 volts divided by 0.005, which is equal to 660x. The first problem can be solved by using an amplifier. Let's see what the second problem is.
In this diagram, we put the shunt resistor in ground path, which makes us able to amplify the voltage across the shunt resistor using a single input non-inverting amplifier. But putting the resistor in ground path is not correct. It may cause many problems in the circuit. This is the second point.
This is a golden rule in designing circuits. We have to try our best to minimize the resistance in ground path. This is why in most power supplies, the shunt resistor is placed on source path. Placing shunt resistor on source path will improve the stability of the load and accuracy of the output voltage measurement. So, the problem of stability of the load and output voltage measurement is solved, but unfortunately it will cause another problems.
When the shunt resistor is in ground path, the voltage here at this point is equal to the voltage across shunt resistor, because one side of shunt resistor is connected to ground and the voltage here is measured relative to ground. But when the shunt resistor is in source path, the voltage here at this point is still relative to ground, but we need the voltage across shunt resistor. So we have to measure the voltage here relative to source voltage. We have to measure the source voltage, then measure the voltage at this point, subtract these two voltages to calculate the voltage across shunt resistor. You may ask why we have to measure the source voltage when we know what the source voltage is. Good question.
Actually, we don't know what exactly the source voltage is. Most power supplies face voltage drop when the load draws current, which reduces the source voltage. Another example is battery-powered devices. The source voltage can be high or low due to battery charge level. So, the source voltage is not known. What we can do in such cases? Here is where the differential amplifier comes into play like superhero to help us.
The easiest way to amplify the voltage across the shunt resistor is to use a differential amplifier. You only need to connect both sides of the shunt resistor to differential inputs, and then the amplifier will subtract these two voltages and multiply the result by the gain value. But there is a problem here.
It seems simple, but it's not, because the source voltage must be connected to input of the op-amp. Not all op-amp ICs can tolerate an input voltage equal to or close to source voltage and work properly. For this purpose, there are special ICs like OPA2992 that should be used. But if you don't have access to these ICs, I can teach you a trick that will allow you to do same thing with regular ICs like LM741 at the cost of slightly increasing measurement error.
I'm gonna use a 20 milliohm shunt resistor, and I will use this DC motor as the load. Look here, this motor draws a maximum of 500 milliamp on 5 volts. So the maximum voltage across the shunt resistor will be 0.5 ampere multiplied by 0.02 ohms equal to 10 millivolts. So to amplify 10 millivolt to 3.3 volt, we have to set the gain to 330x. I'm going to assign 330 kilo ohm to RF and RC and 1 kilo ohm to RA and RB. Notice that the differential voltage here, I mean the input of the amplifier, will be half of the differential voltage across the shunt resistor because of these two voltage divider here. Look here, the output voltage is 65 millivolts. We have to duplicate this value because of the existence of these two voltage dividers here. So we have to divide this number by the gain and divide the result by the value of this shunt resistor. We got this. This number is showing the ampere this motor is drawing. If I multiply the result by 1000, the value is milliampere. This number is indicating 19.6 milliampere, and here the amperemeter is showing 20 milliamperes, which is very close to the number we got. If I increase the load by stopping the motor, you see the output voltage increases.
In the previous experiment, we learned how to use a differential amplifier to measure the voltage across a shunt resistor. In addition, some other sensors produce differential outputs as well. For example, load cell sensors, which are used to measure weight.
This is a 1 kilogram load cell sensor. This sensor has 4 leads. Red and black wires are for excitation to apply voltage. White and green wires are the differential outputs. Inside any load cell sensor, there is a structure like this. This structure is called V-Teston bridge. By applying voltage to these two excitation leads, a tiny differential voltage will appear here. In normal situation, we are expecting this differential voltage to be 0 volts. And when you try to bend this module, or when you put something here, the value of these resistors increases or decreases, and it causes the voltage or differential voltage here to increase or decrease. These are strain gauges inside the module. 2 of them are here, 2 of them are here. These strain gauges are actually a resistor which are sensitive to bending or pressure. When you try to deform the strain gauges, the value of these resistors changes. To use this sensor, we have to fix one side of the sensor, actually this side of the sensor somewhere, and then place the object on the other side to measure the weight of the object. For this purpose, I'm gonna use these 2 pieces of wood and these nuts and bolts. Now I'm able to test the sensor by putting stuff here, like this. These black, green, and red wires here are black, green, and red wires on the module, and this blue line here is the white wire on the module. We just need to apply a proper voltage, mostly a voltage between 3 and 15 to excitation wires, and then the output will be ready at signal outputs. Here in this video I'm gonna apply 5 volts. Here we have 0 volts on white and green differential outputs. When I press the sensor, a tiny voltage appears here. Usually the differential voltage of load cells is very tiny and can't be measured even by using a multimeter. We have to amplify the voltage before reading that. Here I will use 10 mega ohm for RF and RC, 1 kilo ohm for RA and RB. So the gain will be 10,000x. The amplifier is ready, but the sensor is not calibrated. I'm gonna add objects here to make the voltage increase a bit. It is still 0. By adding this, the voltage increases, not that. Yeah. Look here, it is increasing, but by adding these pen caps and some wires, this IC, yes, it's calibrated. It's good. Now the sensor is calibrated, so I can put objects here to see their weight. When I put something here, the output voltage is changed according to its weight. This is the output voltage, and this voltage is relative to the weight of this DC motor.
We can use an op-amp to amplify and read the value of load cells. However, there are specialized ICs for driving them, like HX711. Anyway, I think it's enough for differential amplifiers, and it's time to move on to the last item in the list, which is my favorite. Application number 4, voltage to current converter. The main job of a voltage to current converter is to guarantee that the amount of current drawn by the load is directly relative to a known voltage in the circuit. In the following, I'm going to answer these 3 questions. What is a voltage to current converter? Where in a project will you need a voltage to current converter? How to use an op-amp to make a voltage to current converter?
This box indicates a voltage to current converter circuit. In a voltage to current converter, there is an input voltage and an output current. I mean, the amount of current delivered to the load is related to the input voltage by this equation. K is a constant coefficient. For example, if K is equal to 0.4, Vin is equal to 2 volts, the current passing to the load will be 0.8 amperes regardless of resistance of the load. This is the key point, regardless of load resistance. The circuit will adjust the voltage at output to guarantee the current passing through the load is exactly 0.8 amperes. Let's consider another example. If the K is equal to 0.25, V in is equal to 1.6 volts, then the current at output has to be 0.4 amperes. If the load resistance is 10 ohms, then the circuit will automatically adjust the output voltage to 4 volts to make 0.4 amperes pass through the load. If you replace the load with another resistor, for example a 20 ohm resistor, then the circuit will automatically increase the voltage at output to 8 volts to guarantee a still 0.4 ampere is passing through the load.
Yes, that's interesting. A circuit that tunes output current according to input voltage. So what? What it is good for? Nice question, and the answer is even nicer.
Suppose that in a project you have two parts. In the first part there is a sensor that produces an analog voltage between 0 volts and 2 volts, and in the second part there is a microcontroller that is supposed to display the value of the sensor in the first part and take some actions in some conditions according to the value of the sensor. In a normal situation, it's easy. We just need to connect the sensor output voltage to ADC on the microcontroller and grounds on the both sides together, and then it's okay to microcontroller to read the sensor value.
It will be okay, but what if the distance between these two parts is very far? Say 2 miles, for example. Is it okay to use analog voltage to transfer sensor value to microcontroller? Absolutely not. The resistance of long wires will affect the sensor value. It will reduce the sensor voltage.
The real diagram is this. These two resistors indicate the resistance of wires connecting these two parts. In short distances, the value of these two resistors is negligible and they are not very effective, but in long distances, the value of these two resistors comes into play and they will change the value transferred to the microcontroller. So what we can do? By using a voltage to current converter on sensor side, we can guarantee that the current passing through this path is always function of sensor output. In this example, the load is this constant and known sense resistor plus these two wire resistances. So if we use a voltage to current converter and choose a constant value for the sense resistor here, say 4 ohms, we can guarantee that the sensor voltage will always computable by the voltage across the sense resistor here, no matter how far these two parts are. Because the distance will affect the wire's resistances, while this resistor which is placed on the microcontroller side and the current passing through that resistor, this resistor, are always constant.
Now that the importance of voltage to current converter is clarified, we can consider implementing that circuit. There are several ways to implement a voltage to current converter. Most of them employ an op-amp. Let's see the most simple op-amp based voltage to current converter circuit.
This is the simplest diagram of a V2A converter. In this diagram, I assume that all of these resistors have the same value equal to R, except these two unknown wire resistances. In this situation, the K is equal to 1 divided by R. If you choose 1 kilo ohm for all these resistors, then the K will equal to 0.001, and by applying 2 volts here by the sensor, this circuit will guarantee that 2 milliampere will pass through these resistors regardless of the value of these unknown wire resistances, and the voltage across the sense resistor is always equal to the output voltage of the sensor.
Op-amps are awesome tools for you to drive your designer skills up to next level. Although there are other interesting uses of op-amps, we don't have time in this video to cover them all. I hope to be able to show you more uses of op-amps in another video. Anyway, we have reached the final moments of this video. I hope you enjoyed this video and learned something new. Thanks for watching. If you found this video helpful, please give me a thumbs up, and if you like this video, make sure to subscribe for more.